Welcome back to Math Concepts. In this video we are going to continue working with infinite sets. We are going to look at what the cardinality is for the set of all fractions. In the last video you'll remember we talked about countably infinite sets. Those are sets that are equivalent to the natural numbers and they have cardinality aleph naught. We're going to talk about the cardinality of the set of rational numbers, or the set of all fractions. And we'll also look at a different size of infinite sets. So let's go over to the document camera and look at some examples of these infinite sets. So if we start out with a bit of a review from our last video, you'll remember that any set equivalent to the set of natural numbers is called countably infinite, and it has cardinality aleph naught. There's another property of infinite sets that I would also like to talk about, and that is an infinite set can be equivalent to one of its proper subsets. Okay, so here I have two sets. I have the set that I'm calling E, 2, 4, 6, 8, etc., the set of all even numbers. And here I've got the set F, 4, 8, 12, 16. This is the set of all multiples of 4. All right, if you remember your notation, this is saying that our set F is a subset of E. In other words, every element of F also belongs to the set of even numbers. And it is a proper subset. There are things in the set E, like 2 for example, that do not belong to the set F. So E is a proper subset of F. Actually, I guess some people would get rid of that little line underneath it to denote a proper subset, so maybe we can do that too. Now, as we saw last time, there's a very convenient way to match up the elements. So match the element 2n from the set E with the element 4n from F. Okay, so that is a one-to-one correspondence matching up E with one of its proper subsets. And we can actually use that to show that E is an infinite set. You could not create such a matching with a finite set. If you have a finite set and you're looking at one of its proper subsets, it's got to have at least one less element. There's got to be at least one element that isn't in there, and there's only finitely many, so you couldn't possibly do the matching. So if you take out elements of a finite set, you have changed the cardinality. However, that is not true with an infinite set. You can take out elements of an infinite set and still keep the same cardinality. In fact, this set has cardinality aleph naught. Okay. I also want to discuss the set of all fractions. Okay, so I want to look at this example here. The set of all rational numbers has cardinality aleph naught. And another way of saying what I just said is the set of all fractions is countably infinite. Okay, now I've got a little table written here. Okay, this first row is every fraction that has a 1 in the denominator. The second row is every fraction that has a 2 in the denominator. Every fraction that has a 3 in the denominator, and so on. Okay? So if I eventually went far enough out to the right or far enough down, I would get to any fraction that you wanted me to get to. If you wanted the fraction 12 over 57, I would need to go down 57 rows and over 12 spaces. Okay, but I would eventually get to everything here. Now, if I'm going to do a matching here, what I need to do is I need to avoid staying in the first row. Because if I said, okay, that's the first thing, second thing, third thing, fourth thing, fifth thing, well, this row is infinite. And remember, if I'm showing this as countably infinite, I want to create a matching with the natural numbers. So I would be ignoring all the stuff down here, which is bad. I don't want that. Here's the counting arrangement that we might see here. Okay, so you start here. That gets matched up with 1. And then you go over here. That gets matched up with 2. Now, instead of staying in this first row and getting trapped over there, what we need to do is count in like a zigzag fashion. That's the third thing. Here's the fourth thing. Back up to the fifth, the sixth, and now we're going to count this way. Seventh thing, the eighth thing, and so on. And then we would count on that diagonal. Okay? So we actually could write a formula down for this. I could tell you what position a given fraction would be in this counting. I'm not going to worry about that in this class, though. Just want you to know that the cardinality of the rational numbers has the same cardinality as the set of natural numbers. They both have cardinality Aleph naught. So it might seem like, well, then every set would have cardinality Aleph naught, because here we have infinite this way and infinite this way. Okay, but I'm just going to tell you this as a fact. The proof is actually in our textbook. It's called Cantor's argument. The fact is the set of real numbers, which we haven't really discussed in this class, but the set of real numbers has a greater cardinality than the set of natural numbers. As we know, we have a special symbol for the cardinality of the natural numbers. We call that Aleph naught. The set of real numbers, we call that cardinality C. And the set of real numbers has a greater cardinality than the set of natural numbers. In fact, we could make a whole string of sizes of infinite sets that get increasingly large. We're just going to stick to these two for this first exposure, though. Okay, so the key takeaway here is that if you want to show a set is infinite, you can show that there is an equivalence between the set and a subset. The second takeaway is that the set of rational numbers is equivalent to the set of natural numbers. They have the same cardinality. But the set of real numbers has a bigger cardinality that we're going to call C. Okay, so those are the takeaways from this video.